In this video, we are starting section 6.5 on trig identities. Our goals are to state some common trig identities, then we'll prove one of them, and then we'll do some examples where we have to simplify trig expressions using these trig identities. Okay, all right, so I want to begin by talking about some trig identities that I want you to know for our class, for our precalculus class. Okay, so the first two I'm going to call these defining relations. You don't need to know this term, but I do want you to know these identities. So tangent of theta, I know that using the unit circle, that is y over x. But in the unit circle, y is sine of theta, so the numerator is sine theta, and x is cosine theta. Okay, so tangent equals sine over cosine. You know, this likely you have seen before. Okay, and then with cotangent of theta, well, that's just the reciprocal of tangent. So that would be cosine of theta over sine theta. All right, so these ones aren't too bad. They just come from the definition of what tangent is and cotangent is and plugging in for the y and the x. All right, so then we have what I call the Pythagorean identities. We don't really need to know that term, but I want you to know what these identities are. So we've seen the first one, sine squared theta plus cosine squared theta. That just equals 1. All right, we saw that back in our unit circle section. There are two others that are related to this one, and the way we get the other ones is starting with this identity, sine squared theta plus cosine squared theta equals 1, and dividing both sides by something. So if I divide both sides by cosine squared theta, that's going to help me show this fourth identity, and let's see why. So if I divide the left-hand side by cosine squared theta, then I got to do the same thing to the right side. So 1 over cosine squared theta. Now on the left, I can split this up into two fractions. I'll get sine squared theta over cosine squared theta, my denominator, plus this other term in the numerator, cosine squared theta divided by that denominator, cosine squared theta. So I'm splitting up my fraction into two fractions. And on the right-hand side, well, I know that 1 over cosine theta, that just equals secant. That just equals secant. So 1 over cosine squared theta, well, that's going to be secant squared. That is secant, let's write that squared better. Secant squared theta. All right, and now simplifying the left-hand side, I know sine over cosine is tangent, but here I'm squaring the top and the bottom. So that's going to give me tangent squared. Tangent squared. And then cosine squared divided by itself is just 1. Okay, and this equals secant squared theta on the right. Okay, so now I know what goes into the blank. Tangent squared theta plus 1, well, that equals secant squared theta. Okay, and there's another trig identity. We just proved this one. Okay, there's a similar one I can get that involves 1 plus cotangent squared theta. I'm not going to prove that one. I'll just briefly describe how you would get it. So I just take this third identity, and instead of dividing like I did, so I'm going to divide that third identity. Instead of dividing it by cosine squared theta, I would divide both sides by sine squared theta. Divide both sides by sine squared theta. Okay, and if I do that, on the left-hand side, I'll get 1 plus cotangent squared. And on the right, if I do 1 divided by sine squared, well, that equals cosecant squared. Cosecant squared theta. Okay, so the one that's the most important to remember is this one. The other ones, even if you don't quite have them memorized, the most important thing is to know, how do you get them? Like, you just divide both sides of the first one by something, by cosine squared to get this one, divide it by sine squared to get the other one. Okay, eventually, you're probably going to be using these so much that you'll commit them to memory. Okay. Alrighty, so those are the trig identities that I want you to know for our class. There are a number of other trig identities that you'll probably use in calculus, but we won't really discuss them in our class. Okay, so there are some negative angle identities. Like, for example, what happens when you do cosine of a negative angle? It turns out it's the same thing as if you were to do cosine of the positive version of the angle. There are some double angle identities. Like, for example, sine of 2x equals 2 times sine x cosine x. Okay, and double angle identities involving cosine. In fact, there's a few different forms for these. Okay, so these other trig identities you may see at some point in your calculus class, but we won't really be talking about them too much in our class due to time. I'm really going to focus on the ones that I feel like are the most essential to know, which are these 5. Okay, all right, so let's do some examples. So I want to now focus on how do we simplify expressions using trig identities. Sometimes I really need to use trig identities to be able to simplify stuff. Okay, so if I have 1 minus cosine squared times 1 plus cotangent squared, let's talk about how we can do this. And I'm going to do it in two different ways. So first, I'm going to rewrite cotangent squared in terms of cosines and sines. Like I know cotangent is cosine over sine. So cotangent squared would be cosine squared x over sine squared x. Rewriting trig functions in terms of cosines and sines is often a good strategy in simplifying problems. I don't always do it, but often it can be a helpful strategy. So cotangent squared was the same thing as this. Okay. All right, so now how can I continue this further? Well, I got 1 and I need to add 1 to this fraction, so I'm going to have to get a common denominator. And 1 is the same thing as sine squared x over sine squared x, getting a common denominator. And now I can add these 2 fractions, and when I add them, up top I get sine squared x plus cosine squared x. Okay, oh, and that's nice, because I know sine squared x plus cosine squared x. That's my famous identity. That just equals 1. Okay, so that's quite nice. All right, so what else can I do now? In front, I see this 1 minus cosine squared. And that's looking very similar to my sine squared x plus cosine squared x. So let's see if we can leverage that fact. Okay, so I'm just going to rewrite that trig identity one more time for us. We got sine squared x plus cosine squared x equals 1. And I can rearrange it to get 1 minus cosine squared showing up on one side. Like if I rearrange this, I get sine squared x equals 1 minus cosine squared x. Okay, so now I can take this 1 minus cosine squared x, and I see that that's the same thing as sine squared. So let's replace it with sine squared. Okay, so this equal, let me put an equal sign here. Equal sign, I'm simplifying it. So this first part is sine squared x. 1 minus cosine squared, that is sine squared x. And then that's multiplied by this fraction. And I just got that simplified to 1 divided by sine squared x. Oh, and this is really nice because I see the top and the bottom both have a sine squared, which I can cancel. Ooh, so this simplifies really nicely. I just end up with 1. There's one thing I have to be careful about. Because there was a thing on the denominator that canceled away, I can't forget about my domain restrictions. So this is true as long as this thing on the denominator wasn't equal to 0. So the only way sine squared of x would be equal to 0 is if sine of x equaled 0. So that's what it would take for sine squared to be 0. And okay, so let's figure out when that happens. When does sine of x equal 0? So I'm going to refer to my unit circle. So let me draw some axes. Let me draw my circle. And I know that sine is my y-coordinate. So I know sine is my y-coordinate. And I need to know the points on the unit circle where the y-coordinate is 0. Well, that happens here, right? Because at that point, the coordinates are 1, 0. And it also happens here. Because at that point, the coordinates are -1, 0. So what are the angles at those points? The angle here in radians is 0. And the angle at this other point in radians is pi. All right. So I know the angles that I need to exclude. Because these angles like pi and 0, if x were to equal them, this denominator would end up equaling 0. And that would be bad. That would make it undefined. So overall, my expression just simplified to 1. And I just need to state the condition that as long as the angle, we're calling the angle x, as long as that angle is not equal to either of these angles. Okay, so it can't be equal to 0. It can't be equal to pi. And this problem didn't give me any restriction on the angle. So I can go around the unit circle as many times as we want to. So, and we've seen that when we do that, we need to put a plus 2 pi k after each one of these. So 0 plus 2 pi k as well as pi plus 2 pi k. Okay, that means I can't be at either of these angles, or I also can't be at those angles even if I go around one full time. Like that would put me at 2 pi here. I can't have an angle like that. If I go around again and I add another 2 pi, I would get 4 pi. I don't want to allow angles like that. Okay, last thing that I got to say about this is I need to specify, well, what k is. K is an integer. K is an integer. Okay, so the whole thing just simplified to 1, but as long as I need to include the domain restriction that my angle is not equal to either of these. Okay, because that would have made my denominator be 0. All right, let's end this video. Oh, sorry. I want to end the video with one more example, but I forgot that I wanted to do this first problem another way. So let me show you another way that we could have tackled this first problem. So I kind of deliberately tried to do this problem first, only using the identity sine squared theta plus cosine squared equals 1, because that's typically the one that's easiest to remember. But if we know our other trig identities, like these ones, I see that one of them is going to help me here. I got 1 plus cotangent squared equals cosecant squared. Let's just use that directly. So if I use that directly, my 1 plus cotangent squared, well, that just becomes cosecant squared. That just becomes cosecant squared. Okay, and then from before, I know that 1 minus cosine squared. We did that over here. Well, I know that that equals sine squared x. I got sine squared x. And cosecant squared, well, that is 1 over sine squared. Okay. Oh, and now it's going to be exactly the same as before. The sine squareds are going to cancel. Sine squareds are going to cancel, and I'll get 1. I'll just have to make sure to remember this domain restriction and think about what angles would have made sine be equal to 0. Okay. So I would say method 2 ended up being a little bit faster. But the difficulty with that method is I do have to remember a more complicated trig identity, that 1 plus cotangent squared x equals cosecant squared. Okay. All right, so let's end this video with one other example. So let's say I want to simplify the following expression, cosine x over 1 minus sine x, and the whole thing is being subtracted by secant x. Okay, so first what I want to do is I want to give you an opportunity to try this. So pause the video for about 4 minutes and try this one on your own first. So pause it in 4, 3, 2, 1. Pause it and try this one on your own. All right, so hopefully you did that. Hopefully you paused it and tried it on your own first. Let's bring it back together and let's talk about this. Okay, so let's see, what can I do here? I know secant x is 1 over cosine x. So let me rewrite it. That's 1 over cosine x. Okay, and now I'm subtracting two fractions, and I can get a common denominator to do that. So I would need to multiply this first fraction, top and bottom, by the other denominator. So cosine x over cosine x, and I multiply my second fraction, top and bottom, by the first denominator, 1 minus sine x, and then over 1 minus sine x. All right, so now when I do the multiplication, these first two fractions multiply to, I get cosine squared on the top. I'm going to leave the denominator factored as 1 minus sine x, parentheses times cosine x. Because if something cancels later in the problem, it's helpful to leave that thing factored. All right, and then multiplying out my second set of fractions. The numerator, 1 times something is just the something. So I get 1 minus sine x. And that denominator, I'm going to leave it factored as cosine x times 1 minus sine x. Okay, so I got a common denominator. Now, to subtract these fractions, remember this negative sign, it's got to distribute to each one of these terms in the numerator. Okay, so if I do that, I get one fraction. I'm going to get one big fraction. Cosine squared x, and then distributing that negative, I'll get minus 1, and then plus sine x. All right, and leave my denominator factored as 1 minus sine x, that whole thing in parentheses, times my cosine x. Okay, so I've gotten a common denominator. I've turned it into one fraction. What can I do now? Well, one of the things I want to notice about this is I'm seeing, let me highlight this, I'm seeing a cosine squared x minus 1 show up. And that reminds me of this identity a little bit. Sine squared x plus cosine squared x equals 1. So can I rearrange that identity a little bit to make it look like what I have, cosine squared x minus 1? And the answer is yeah. So what would that look like? If I rearrange it to make it look like this, I have to multiply both sides by -1. Or I could think about it as I'm going to move this whole right-hand side over to the left-hand side, because that would give me positive cosine squared x, and then -1. And then move the sine squared x over to the right to equal negative sine squared x. Or the other way I could have gotten that is just multiplied both sides by -1, and it would have given me the same thing. Okay, so cosine squared x minus 1, well, that just equals negative sine squared x. So let's replace it with negative sine squared x. So I got my negative sine squared x. Let me highlight that. And then I still have that plus sine x on the numerator. That whole thing divided by 1 minus sine x times cosine x. All right, so now I see both of the terms on the numerator have a sine x. So in common, so let's factor out a sine x. If I factor out sine x, then from the first term, I'm left with minus sine x. From the next term, I'll be left with plus 1. Okay, and then all over my denominator, which is 1 minus sine x times cosine x. And now that's nice because I see the same factor on the top that I do on the bottom. Okay, I got that minus sine x plus 1. Those are the same, so they cancel. So I'm left with sine x divided by cosine x, and that just equals tangent x. Okay, and then because I did cancel a factor on the denominator, I can't forget the domain restriction that comes from it. So this is true as long as this thing down here didn't equal 0. And that would happen if sine of x equaled 1. So I want sine of x to not be equal to 1. So let's figure out what angles would make that happen so I can exclude them. So overall, this just equal tangent x. As long as, so what would my angle x what would I not want it to be? So where on the unit circle is sine equal to 1? Like I know sine is my y value. So on the unit circle, sine is equal to 1 at this point up top, 0, 1. And what's the angle up top? Well, that angle is pi over 2. So the angle that I want to exclude is pi over 2. And then do I need to do the plus 2 pi k thing? Well, yeah, because in this problem, it didn't restrict my angle x. Like I didn't say x is just between 0 and 2 pi. So I can go around as many times the unit circle as we want. So I got to do pi over 2 plus 2 pi k. I want to exclude all of those possibilities. And then I should say k is an integer. All right, and there we have it. It's simplified to just tangent x, but I need to include this domain restriction so that my denominator isn't equal to 0.